So this is MathStat341, day 27. What I want to do today is talk about generating functions. And we're going to start first with a generating function, and then we're going to look at a close cousin of the generating function, the moment generating function. And this is going to continue our quest for trying to find a good way to do algebra. And not surprisingly, different choices will lead to different types of algebra, and some will be easier to get at what we want. The homework for the rest of the semester is going to be significantly less than the start. There's going to be some more advanced material. I want you to get to the point where you have a sense of what's going on. There will almost surely be an exam question asking you to prove the central limit theorem for specific distribution following arguments we've done in class, something like that. The exam that you have right now, none of this material we're doing right now is on that exam. All right, so generating functions. You've seen some before. We did the Fibonacci's. And we did, f of x was the sum fn x to the n, and it had a nice closed form expression. It was something like maybe x over 1 minus x squared, something like that. And from that closed form expression, there was a lot we could deduce. More generally, GA of S is going to be the sum, and goes from 0 to infinity, of AN S to the n. There's a lot of different things we can look at. This is good notation. G stands for generating. And the A is because it's associated to the sequence A. We could look at GB of S would be the sum of Bn S to the n. And then the thought is there should be some sequence Cn such that if we multiply these two, we'll get a new sequence. So this should be the sum, and it goes from 0 to infinity, of Cn S to the n. And if you think about this, what's really going on is we have A0 plus A1s plus A2s squared times B0 plus B1s plus B2s squared. And when we multiply, we basically promise to take real analysis in the future and not worry about conversions. A0 times B0, that will be the constant term. Now, how can I get a term of size s, just one s? How could I get that?
A0 times A1s or A1s times, or A naught times.
Yeah, I would do A naught times B1 plus A1 times B0. Now, how can we get an s squared term?
So I guess we can just kind of like in generally like look at the subscript, and then like if the subscripts add up to 2,
yeah.
that's squared.
So the next one would be A0 B2 plus A1 B1 plus A2 B0 s squared. And so in general, Cn is going to be the sum of AK Bn minus K. K goes from 0 to n. Does this remind you of anything? Convolution. And so we will define this as A star B. If we take the convolution of the sequences A and B, then we will define it like this. And now our theory of convolutions should hopefully be applicable. And this should show us that this might be useful in probability. Now we have, for the most part in this class, we've only looked at pure probability distributions. Either they're discrete or they're continuous. We're not looking at really mixed things. So right now I'm focusing on the discrete stuff. We could focus on continuous stuff as well. There's a lot of results you can prove about generating functions. So, one of the biggest questions is, if I give you a generating function, does it uniquely determine the sequence? Well, if I'm doing something like this, if I give you the series expansion, if GA of S equals GB of S, then the sequences A and B have to be the same. And one way to see this is, well, what's the best value of S to take to compare these two? Not 1. Because if you take 1, you have to add infinitely many terms. So it should be 0. So if I take S equals 0, the only term that survives here is the A0. The only term that survives here is the B0. So if they're equal for all values of S, A0 equals B0. And then what you do is you subtract A0 from this, divide by S, and you have a new series. And then when you set S equals 0, you get A1 equals B1. And you can continue like this and say, if the two generating functions are the same, then the series are the same. And that's a great thing about discrete sequences like this. So we'll call that a theorem. So GA of S equals GB of S if and only if A equals B. And we'll always assume we're in a situation where things converge. It is not always the case that things are unique. So we've talked a little bit about the worst or one of the worst functions in all of mathematics, or if you want, one of the best functions in mathematics, depending on your point of view. This function, I'll do b of x for Baz, is e to the minus 1 over x squared if x is not 0, and 0 if x is 0. This function has all of its derivatives at 0 equal to 0. So if you try to write the Taylor series of this function, the Taylor series is identically 0. Oh dear. The only place where the Taylor series agrees with the original function is when x equals 0. This is not something to celebrate. You write the Taylor series as the value at 0 plus the first derivative at 0 times x plus the second derivative at 0 over 2x squared. Well, when you put in x equals 0, you force all of these terms to be 0. It has to agree with the function at 0. You forced it to agree. That's the only point where they agree. The radius of convergence is 0. The truly nightmarish thing about this function is the following. Who believes they understand how my mind works? I'm thinking of a function, and the Taylor series is 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. What function am I thinking of?
Is this the cosine?
Almost. It's cosine x plus 1701 phi of x. So close! If I compute the Taylor series of this, I do get 1 minus x squared over 2. So a Taylor series does not uniquely determine. For cultural extra credit, why 1701?
Is it a significant year?
It is a significant year. On this campus, I might say 1792. So Yale was founded in 1701, where I went to school. Any science fiction fans? NCC 1701. If you want, you can put either the letter A, B, C, D, or E, and I think they've gone up to F. Oh, so sad. The Enterprise. So the whole point is just to demonstrate it's something arbitrary. If you want, I could be more literary, and I could do 24,601. If you want to be a little bit more literary. Doesn't matter what I put there. I can't detect it. This is one of the biggest problems, and this is what's going to make proving the central limit theorem painful, is we need to be able to determine what's going on, but there's many different things that have the same Taylor series. There will be many different probability distributions that have the same series of moments. There's a great problem, can you hear the shape of a drum? If you can hear the different vibration frequencies, is this enough to determine the shape? The answer is no. You can have different drums that actually have the same resonances. Okay. So this is what's going on. We want to determine what is a good choice of the A's to make this valuable for probability. So let's say X is a random variable. And we'll say it's discrete. Anybody want to give me a choice? Say 0, 1, 2, would be the values it takes on. Anybody want to give me a choice for AN? What might be a good choice for AN? Should be something related to this discrete random variable, which takes on the values 0, 1, 2, 3.
0.
So I could make it identically 0, but then that would be the same for all distributions. So I want something related to X and something related to N. So what would you have related to X with N?
Just like an X plus N or X times N.
Well, but X is my random variable, so I don't know what X plus. What property of X might you associate to the number N?
Like maybe the PDF of X, like the probability
Yeah.
that it's
The
that
probability
X equals
that X equals N. That's a natural thing to associate to your random variable, right? If I give you my possible values of 0, 1, 2, 3, 4, let's let AN be the probability X equals N. So that I can say Gx of S is going to be the sum, and goes from 0 to infinity, the probability X equals N times S to the N. Does that look like anything to you? Does this remind you of anything you've seen? Yes. And so I'm impressed you saw that without my doing this first, which I have to do many years. Right, it is S to the N probability. Does that look more like an expected value now? We have the value times the probability of that value. So this would just be the expected value of S to the N. So that is my generating function. Okay? Let's explore some consequences of this. And again, you can do generating functions for more than just probability distributions. The very first thing, which we did much earlier in the semester, was we looked at the generating function of the Fibonacci's. And so we've already spent some time, we've seen how valuable it is. We got René's formula from that, which was wonderful. Now that we have generating functions, we have the generating function of X. So once we have the generating function of one random variable, what might we do next? Do it for another. So what should the relationship between be X and Y? X and Y are independent, right? Independent random variables. When in doubt, make your random variables independent. Things are much nicer. And then we could say Z is X plus Y. The generating function X times the generating function of Y is the generating function of Z. We'll call that 4. Now we've got to be careful as to what are we doing this for. Technically right now we're only doing it maybe for discrete distributions. But you can see the convolution coming in, and in fact, this tells us how we should define the generating function in general. The generating function was the expected value of S to the X. So as long as this converges, let's use that as our definition of the generating function. So use Gx of S, oh, I guess I'll use U, is just the expected value And so we need these to converge. Assume all converge. Now, there's a lot of ways to prove this. One, especially if we're in a case like this, we can just expand everything out, and we'll see the convolution coming in. But there's a much nicer way. Let's look at the expected value. We'll do g of z of s is the expected value of s to the z, which is the expected value of s to the x plus y. Well, what is s to the x plus y?
It's just
Sorry.
s to the x, s to the y.
Okay, now what can we do?
Separate them.
Separate them. What allows you to separate them?
Independent.
The independence. So because they're independent, it's the expected value of s to the x, the expected value of s to the y, and that's just gx of s, gy of s. And there's the proof. What if you had more than two random variables? Yeah, I'm not even going to bother writing it on the board, right? If I had a sum of 3, 4, or sum of n random variables, the generating function of the sum is the product of the generating functions. Oh, that's nice. So if independent, the generating function of a sum is the product of the generating functions. Okay. Yes?
How would you do it if they're not independent?
Got me. Because if they're not, if they're not independent, you would have to go back to the definition. The problem is if they're not independent, if y is negative x, then it's always 0. If y is x, you've just doubled your value. So depending on what the dependency is, I know there's a lot of dependencies, but that's what the Department of Redundancy Department insists we do, you're not going to be able to get a nice clean answer. It's going to depend crucially on the dependence. And this is one of the reasons why we really love independence. It makes these calculations so much nicer. Now we could of course also, instead of having just x and y, we could have alpha x plus beta y. We could play games like that. And we will do games like that later. But we're going to do it more for the moment generating function. Is there anybody here who has seen the Fourier transform? Right. If you have seen the Fourier transform, then I have to be a little bit careful. Because in probability, the probabilists like to talk about moment generating functions and characteristic functions. Analysts like to talk about the Fourier transform. They are essentially the same with a change of variable. The difference is the characteristic function, the moment generating functions, do not always exist. The Fourier transform will always exist. It is much nicer to work with a quantity that exists. But you need to know complex analysis. And so it's a good trade-off. And I will say a little bit more about that. I might even give a little sketch about how complex analysis works. We've got some time this semester and just give you a quick crash course. This would not be on the exams. This would just be to give you a sense of what's out there. So we have a lot of wonderful stuff. We can try to calculate some generating functions. You want a good function where the generating function will exist. Now what might be the case is the generating function exists for some choices of s, but not for others. So can somebody give me a nice continuous function that you might want to try this on? So
Exponential.
Exponential is great. It's one-sided and it has good decay. So let's let x be exponential with parameter lambda. So f of x is 1 over lambda e to the negative x over lambda for x greater than or equal to 0. We will use the good notation. If I want to calculate the expected value of s to the x, this is just a generating function, This is going to be the integral from 0 to infinity, because I don't need to worry about negative values because the density is 0 there. I will have s to the x, and then I will have 1 over lambda e to the negative x over lambda dx. All right, now we need to do this integral. How should we handle the algebra? What should we do? What kind of function is s to the x? Is this a polynomial? No, what kind of function is s to the x?
It's an exponential.
Yeah, so we should write note s to the x equals e to the x log s. And if we do that, we can combine. And we get 1 over lambda, integral from 0 to infinity, e to the negative x, and then what do I have? I have 1 over lambda, and I have log s. So I get 1 over lambda minus the log of s dx. Now I'll use the bad notation. If I have the integral of e to the minus ax, if I multiply by a, it integrates to 1. So I multiply by 1 over lambda minus log x, and then I divide by 1 minus lambda. So this is the same as 1 over lambda, do it very slowly, 1 over lambda minus 1 over log s, integral from 0 to infinity, 1 over lambda minus log s, e to the minus x, 1 over lambda minus log s dx. What does the integral equal? What will this integral equal? So I've got a e to the minus ax dx.
The integral of e to the negative x.
Yeah, and what's the integral of e to the negative x from 0 to infinity? You change variables. This is the integral of e to the minus u. It just increases to 1. That's the whole point of playing games like this. If you have something where you can note that the functional form is a probability distribution that you know, just make sure that the constants are right. And then you don't have to bother doing the integration. Ah, this is just an exponential written in the notation Professor Miller hates. But, my hatred, for my convenience, I'm happy to consider it. It's, it's either that or do the integration, and I don't know. It's cold, please stay down. So I pull the lambda in over here, and I get 1 over 1 minus lambda log s. Hopefully I've done everything correct. And so this is the moment generating function. The generating function. So the question is, does this converge for all values of s? What do you think? So I want to know what values of s is this well defined. If I want to do this integral, what must be true for this integral to converge?
S can't be 0.
I'm sorry?
S can't be 0.
Okay, so if s is 0,
Oh, I guess we already. Oh.
well, no, but so we definitely want to make sure that s can't be 0. Good. What else?
Lambda.
Well, lambda is going to be our fixed parameter. Yes.
1 minus log s can't be 0.
1 over lambda minus log s.
Yeah, 1 over lambda minus
So
log
what do we need to be true about 1 over lambda minus log s must be what? It's more than just not 0.
Oh, greater than
It's
0.
got to be greater than 0. If this is a negative number, we're integrating something like e to the 7x. Yeah, exactly. Run right. But if this is a positive number, then we're fine. So we need 1 over lambda minus log s to be greater than 0, or we need 1 to be greater than lambda log s. If we exponentiate, we get e to the 1 over lambda greater than s. Oh, have I done things correctly? Yeah, okay. And what else do we need to know about s? We also need s to be greater than 0. Because if s is 0, the log of 0 doesn't make sense. But the smaller s is, you think of s as 1 over a billion, then that's going to be the log of 1 over a billion. That's going to be a very negative number. This negative makes it a positive, that makes it a negative again. So good, that will contribute to decay. So the answer is reasonable. And what you could then do is you could say, well, I wonder what would happen if I added an exponential to an exponential. If an exponential plus an exponential was an exponential, then I would have to get 1 over 1 minus lambda 1 plus lambda 2 log s. And I'm not going to get that. I'm going to get 1 over 1 minus lambda 1 log s times 1 over 1 minus. So we can immediately deduce exponential plus exponential is not exponential. If we did a Poisson, we should actually be able to see things work. So who wants to do Poisson? I'm happy to do it, I'm happy not to do it. Does anybody want to see Poisson? Sure, okay. So oftentimes first loud voice works, if there's no loud voice, first semi-indifferent voice wins. Let's do Poisson. So x is Poisson with parameter lambda. So that means the probability that x equals n. Do we have anybody here who knows what the Poisson is? Sadly, there's a certain person who would have been wonderful to have here today, but oh, can you fill in for them?
Yeah.
Oh, excellent, excellent, excellent.
X lambda.
No, not because I'm using
I'm
using math notation.
So
N to the lambda.
E to the negative n or
Not n.
n. What about?
I'm using lambda as my parameter.
Yeah, so negative n.
Oh, so wait.
It's lambda to the
Lambda to the n. E to the minus lambda over n factorial. It's hard when you use different notation.
Yeah.
And when you use x versus n and flipping them back and forth. So this is the probability that x equals n. So if I wanted to calculate the generating function.
I also use mu as my parameter.
Right, I know, which is just.
It was what happened in the paper, so I tried to.
I know, and that's the best thing to do is when you're using someone else's, you follow them. My brother is an engineer. Do you know how my brother pronounces the square root of -1? J. Engineers use J for the square root of -1 because for them, I is current. And so when my brother and I have conversations, it often takes us a while to just translate it to what the other one is saying. So this is going to be the expected value of s to the x. So this is going to be a sum and goes from 0 to infinity. So we're going to get s to the n, lambda to the n, e to the minus lambda over n factorial. And now it's all about doing the algebra. And if you're really quiet, you can hear some of the algebra wants to be done. What wants to be done?
Combine S and lambda.
Yeah, s and lambda, they really want to be together, don't they? The e to the minus lambda, that's independent, so I can pull out e to the minus lambda, and I have a sum and goes from 0 to infinity of s lambda to the n over n factorial. Oh, but what is s lambda to the n over n factorial? That's just, it's just, I'm sorry?
E to the S lambda.
Yeah, so I get e to the minus lambda, e to the s lambda, and so this simplifies to e to the lambda 1 minus s. And now what's really nice is if we have xi is Poisson with parameter lambda I, then say x lambda 1 plus x lambda 2, if we look at the generating function, well, the generating function of a sum is the product of the generating functions. So we get e to the lambda 1, 1 minus s, e to the lambda 2, 1 minus s. This is e to the lambda 1 plus lambda 2, 1 minus s. And we see that Poisson plus Poisson is Poisson with parameter lambda 1 plus lambda 2. So this is the benefit of looking at these discrete random variables where the generating function does uniquely determine. The generating function does not always uniquely determine. But in the case of discrete random variables taking on the values 0, 1, 2, 3, it does. And now we get Poisson plus Poisson is Poisson. So that's a really nice result. That's another way to see it. So we can do this for a whole slew of different things and just do the calculations. So this is Calc 2. Can you do these integrals? Or can you do these sums? Okay. The generating function is nice, but it turns out it's not as well suited for the calculations we need to do as something else. And again, a huge part of this course is trying to learn what is the best way to do the algebra. So I'll try to keep the generating function defined over here. And we're going to look at something called the moment generating function. Now you should have read about this in the book, but if you hadn't, you should be able to fake it. What do you think the moment generating function will generate for you?
The moment.
Yes, if it's not the moments, then this is poorly named, right? You should have good names. Moment generating function gives you the moments. And to some extent, it should be pretty similar to the generating function. But it should be better for algebra. And that's the whole point of a lot of what we're doing, is we're trying to find what is going to make the algebra as easy as possible. The more problems you do, the easier it is to figure out how to do the algebra. When you're starting, it's a real challenge. So the moment generating function. And in a structure, it's abbreviated MGF, right? So the generating function of x at s is the expected value of s to the x. The moment generating function of x at t, we use a different letter. Yes, thou shalt not use s. Probably because the moment generating function is nicer and I'd much rather write a t than an s, because s's can look like 5s. It's the expected value of e to the tx. What do you think? Are we doing anything new, or am I doing like smoke and mirrors and just dressing up a pig to make it look nice?
Dressing it up.
I'm dressing it up. So how do you get from one to the other?
Because s to the x is ex.
So s to the x is basically e to the tx. So what's the relationship between s and t?
T is the log.
So you could say t is the log of s, or s is e to the t. Does it really make a difference if I study generating or moment generating? No. And in fact, we should be able to get a lot of results from moment generating functions immediately from results from generating functions, because they have this nice relation. So similarly, if x, I are independent, the moment generating function of x1 plus xn of t should be the product, k goes from 1 to n, of the moment generating function of xi of t. And you should be able to get this immediately by just converting to generating functions, by just taking s to be e to the t. Or you could go back into the definition here and just play the same game and do the same proof. But it comes immediately. Later, we're going to want a slightly refined version of this where I allow myself to put some constants here and just see how things change.
Would it be x to the x subscript k?
Ah, yes, k, I'm sorry. I was trying to avoid I for a reason. Thank you. So, I avoided I. Sometimes people look at the characteristic function, which I believe is often denoted maybe px of t is the expected value of e to the I tx. Is there much of a difference? No, I just replace t with I times t. The difference is e to the I theta is cosine theta plus I sine theta. The absolute value of e to the I theta is 1. So what that means is this always exists for all values of t. For any real t, this exists. So it exists for all real t. This function might not exist anywhere. We have exponential growth. So I could have a probability distribution function that's decaying slowly. Let's take the Cauchy distribution. The Cauchy decays like 1 over x squared. Well, when t is positive, it's going to be total. But actually for t negative, it'll be fine. So for the Cauchy distribution, the moment generating function will exist for t negative, but it will not exist for t positive. We will need moment generating functions to exist in a neighborhood about the origin. And so for us, the moment generating function must exist in a neighborhood about the origin. For the Cauchy distribution, it does not. Okay? What are the big conditions for the central limit theorem? We want mean to be 0. Okay, that's just adjusting. We want the variance to be 1. Okay, that's just adjusting. Any finite mean and finite variance would work. And then sums of independent copies become normally distributed. The Cauchy distribution fails. And not surprisingly, Cauchy plus Cauchy is Cauchy. The best way I know how to show that is to use complex analysis. I think you can do it just using Calc 2, by just doing some maybe slightly painful trig substitutions. It's been a while. But we do know the antiderivatives involve the arctangent. I think you can do it. Complex analysis is just nicer. So we have this moment generating function. I've given you the definition. What would you like to be able to get from the moment generating function? Moments, right? If I can't give you moments from the moment generating function, what good is it? Okay, now if you look at just the generating function for a continuous random variable, it's not really clear what we're getting. Let's look at the moment generating function. Anybody here see the great physics hats they have? Imagine I put on it's more of an engineering hat than a physics hat, but I put on my hat where I can just do math fast and loose, and I don't have to worry about justifying what I'm doing. And I forget that I am a professor of mathematics. And I'm saying, this is a pre-core math stat class. You're not supposed to have seen real analysis. Let's just play with the math and see what we get. So this is equal to the expected value of e to the tx. So this is the integral from minus infinity to infinity of e to the tx times the density function. When you see e to the tx, what do you want to do to e to the tx?
Separate
How?
e to the t times e to the t. Or change it into the s.
Well, that's not going to help us do anything. We want to get the moments. Right? Moments would be integrating, x to the n against this. What could I do to e to the tx?
Oh, it's not addition. It's e to the t
Right,
up to
right, it's e to the t times x. So they're all together right now. So what could you do to the exponential? What could we
Take the log.
inside? You can't just take a log inside. Are you mad?
You can do e to the t and then take the exponent to
And then raise that to the x. But how do I raise it to the x power? the exponential? What do you know about the exponential?
Oh, we can find like the generating function for the exponential.
Not really, because it's tied up in here. We want things like the integral from minus infinity to infinity of x to the n. Right, because if we had that, that would just be the nth moment. We want something like that, but we have e to the tx. So we've got to somehow change this but leave that constant. What can we do to e to the tx? Again, I'm talking about playing fast and loose with the math. What can I replace e to the tx with? It's got to be something equivalent to it.
X to some exponent.
Not x to an exponent, because it's an exponential
Okay.
of tx. What can I replace e to the tx with?
The sum of
Yeah.
x to the n over.
So this is the same as the sum, n goes from 0 to infinity, of t to the n, x to the n, over n factorial, right, times the density. So I really want to try to emphasize why we're doing what we're doing. Now when you look at this, the integral of the sum is not always the sum of the integral, but it is today. So I would just say it's the sum, and goes from 0 to infinity, and now I can pull out the t to the n over n factorial, because that has no x dependence. And I'll have the integral from minus infinity to infinity of x to the n times the density.
Oh.
Yeah. And now notice we see exactly what we wanted. So this is just going to be the sum, and goes from 0 to infinity of mu n t to the n over n factorial. And the hope is the n factorial is going to decay so fast that this will converge for values of t. And this is why this is called the moment generating function. So if I take the moment generating function at 0, I just get 1. If I take the derivative of the moment generating function at 0, I get mu1. If I take the second derivative of the moment generating function, well, I'm going to get a 2 coming down twice. That's going to cancel the factorial. I'll just get mu2. And that's why the n factorial down below is actually nice. When you take the derivatives, things are beautiful. So if you want to calculate the moment of a distribution, if you know its moment generating function, just take a derivative and evaluate.
Wait,
So, yes.
It's so much easier than like using, like calculating it all.
Yes, in many situations, yes. But you were young earlier in the semester. You are now older and wiser, right? And you can appreciate this, right? Also, you have to be able to do the integration. You have to be able to do the summation. You remember, you suck at integration. I do too, we all suck, okay? I'm not singling you out. Humanity is terrible at integration because most functions don't have a nice antiderivative. So if you can't get a closed form expression, this is helpless. But if you can, so we could do the Gaussian, we could do the exponential. So we're running a little bit short on time. Can somebody recall for me if x was relative, if x was, exponential with parameter lambda, then the generating function of x was just 1 over 1 minus lambda log s. And so the moment generating function of s, so we have s is equal to e to the t. So log of s is just equal to t. I'm just saving myself time, right? We calculated the generating function of the exponential. I could do the integration directly to calculate the moment generating function. But given that I've already done it, let me just convert. It's 1 over 1 minus lambda t. So now we just take derivatives. No, I don't want to take derivatives. What can we do? When you see this, what should you be thinking?
Taylor's series.
Log, Taylor series. What do you mean by Taylor series?
Because that tells us the value of the derivative.
Okay, so how would you calculate the Taylor series for this? We have 1 over 1 minus lambda t.
It's a geometric series.
It's a geometric series, right? Geometric I equals lambda t. You know, when in doubt, I am lazy and I don't want to do calculations. So I know this is just 1 plus lambda t plus lambda squared t squared plus lambda cubed t cubed plus dot dot dot. And then somebody in the class will go, but Professor Miller, it doesn't have the n factorials down below. Fine. 1 plus lambda t plus 2 lambda squared over, I'll do it this way, 2 lambda squared over 2 factorial t squared plus 6 lambda cubed over 3 factorial t cubed plus dot dot dot. And now it's set up so I can immediately conclude that the expected value of x is just lambda. The expected value of x squared is just going to be 2 lambda squared. So the variance of x is just going to be the expected value of x squared minus the square of the expected value is just going to be lambda squared. So the standard deviation, and there you go. There's our values for the exponential random variable immediately. We didn't even really need to take derivatives, right? This is the power of knowing algebra and being comfortable with algebra. Always, always, always think about, I can either do the quadratic formula, or I can sometimes just look and see the answer. If you can look and see the answer, is that better than the quadratic formula? Yes. If you can't just look at it, is life no longer worth living? No, you just use the quadratic formula. In the greatest scheme of things, is it horrible to require you to use the quadratic formula? No. It's the same thing for this. If you had to differentiate this, is this an onerous task? If you feel yes, then you're in the wrong class. Okay? This is a 300 level MathStat class. I'm saying taking 2 derivatives of this function with respect to t, that is a very reasonable thing to ask. Okay? If you, however, notice that it's a geometric series and you expand it out, you can avoid having to take the derivatives. The more ways we know how to do a calculation, the better. And so over here, this is truly wonderful. Remember we did multivariable Taylor series earlier in the semester, and we had the sine of x plus y. Just take the sine of u and then replace u with x plus y. And then that bypasses a lot of the technical stuff in multi that you probably never even did. It's the same way over here. We can often bypass the derivatives by just noting stuff like this. All right, so I just want to talk briefly about Monday's class. Monday, we do have class on Monday, I believe. Williams does not have Monday as a holiday.
Yeah.
Right. Right, so we have class on Monday. So Monday, anybody know what day it is?
Veterans Day?
It's Veterans Day. So in my operations research class, we will be doing the German tank problem, which is a great application of probability and statistics. I would do that in this class as well, but my kids may be here for either one or both of the classes, and so I will probably do that lecture later. And so instead we will do the M&M game. So we will bring in M&Ms to eat M&Ms and learn mathematics by eating M&Ms. I can't do this in my kids' classes because it is illegal to bring food into the schools. But here, this is college. This is one of the advantages we have. So on Monday, we will do the M&M game. And it is how my kids got their British number of 3.